complex means poles lies on the imaginary axis. Let it be, this one is S1, one S2, this is S3, this is S4. In this case, the system is, yeah, correct, marginally stable. So if there exist non-repeating poles on the imaginary axis, we can call it as a marginally stable system, because for some set of bounded input, it will produce bounded output, but some other bounded input, there is a chance of unbounded output also. So that kind of system can be called as actually not only marginally stable or unstable, because both possibilities are there, right? So one more observation we have find out that what is the frequency of oscillation for this kind of system. If a pole exists in the imaginary axis, let it be plus J1 and minus J, the frequency of oscillation also equal to 1 radians per second, right? So this is equal to the pole, real value of the pole. So only when that we'll go back to this problem. One more point I have to click that. Which one is that? Yeah, here, see, our system is 1 divided by x square plus 1, right? So our poles are at s equal to plus or minus 1j. One is this, one is this. Okay. So what is the frequency of oscillation? It is omega equal to 1. So if your omega is not equal to 1, what will happen? The system will go to unbounded condition. Here one more condition is there. See, here I have done that as t tends to infinity, y of t remains bounded only when omega is equal to 1 radians per second. Anyway, we will see the MATLAB simulation. By the time you can see it. Otherwise, you can do some analysis also. If you put omega equal to 1.1 radians per second, it will be an unbounded state. So the condition is omega is not equal to the 1. Okay, that also keep in mind. Another thing is one more observation. 4 point. Suppose these out of these 4 poles, I have S1 and S2 at the same point. Again S3 and S4 at the same point. S1, S2, S3, S4. And if we have repeating poles on the imaginary axis, then we can call the system as unstable. So these are the 4 important points we have to keep in mind. The conclusion is the location of the poles of a system which determines the stability of the system. Hope everyone understood the concept. So we will move to the next topic. Now in our transfer function, we have not only have poles, zero also there, right? So we need to study the effect of zeros also. So next topic is effect of zeros. Okay. So for that, we can do again. We can select some system and do our analysis. So you can select this transfer function. So consider this transfer function t of s is equal to y of s divided by u of s, which is equal to 1 divided by s plus 1, s plus 10. So first of all, we will consider a system which does not have any zero. it is having only pole, right? So in this case, we can write m equal to 0, n equal to 2. Since n is greater than m, we can call it as a strictly proper transfer function. Another observation is, since n equal to 2, the order of the system is 2. So it is a second order system. So first of all, we will see the step response of this system, which does not have any order. Okay. So how will you find out the step response? Unit step response. So U of s is equal to 1. So we can write Y of s is equal to 1 divided by s multiplied by s plus 1, s plus 10. So applying partial fraction, we can write it as a by s plus b by s plus 1 plus c divided by s plus 10. So after, how can you find the residues? Please find the residues and tell me what is a, what is b, and c. What is a? One by 90. Yeah. Okay, fine. So we can write y of s is equal to 1 by 10s minus 1 by 9 s plus 1 plus 1 by 90 s plus 10. So after taking inverse Laplace transform, you can obtain the unit step response, that is 1 by 10 minus 1 by 9 e power minus t plus 1 by 90 e power minus 10. So this is the observation. This already we know how to do it. We have done the same analysis for some other problem, right? So what are the observations? How can we draw our poles in this plane? So if we take, this is real, this is imaginary, and we have two poles in this system. One pole is at s equal to -1, other pole is equal to s equal to -10, right? This is at -1, one pole is little bit far, is -10. Okay, so you can see the same observation. We have two exponential terms. The exponents of these two exponential terms are the poles, right? Okay, fine. So one important observation is here. You can see, if we take these two exponential terms, so this is one of the exponential term, and this is the another exponential term. Okay, in this case, what is the steady state value? One of the observation is steady state value is 1 by 10, right? Because e power steady state, how will you find out steady state value? If t tends to infinity, these two times will be 0. So finally you will get y of t is equal to 1 by 10. That is the one observation, right? So if I take this term 1 by 9 e power minus t. Okay, how can you draw this term with respect to t? Taking t on x-axis, this can be in y-axis. So at the time t equal to 0, what is the value? 1 by 9, right? So let it be in somewhere here. 1 by 9, and it is an exponentially decaying function. If t tends to 0, it will slowly exponentially it will decrease and it will go to 0, right? So that will be the nature of this term 1 by 9 e power minus t. What about this term? Is 1 by 90 e power minus 10t. So 1 by 90 is again it will be very low compared to this rate. So it will be closer to some 0.1. It will be 0.01 closer, right? So it will be some from here 1 by 90. That is also an exponentially decaying term. It can be like this. So what do you understand from this? You can see that out of this two exponential term, this term is dominating the output, right? Because this is, you can see while seeing the FN directly, you can observe that this term is dominating the output response. Okay, so this term, in the sense, this term is referred to the pole -1. So you can see that the pole -1, which is very closer to the imaginary axis. You can see that if you compare it with 10, the pole -1 is very closer to the imaginary axis. So in other way, how can we conclude it is the pole which is closer to the imaginary axis, which have more effect on the output, right? So we can call this kind of poles as dominant poles. Dominant poles. So what do you mean by dominant pole? The poles which are closer to the imaginary axis, you can call this pole as dominant poles. Why? Because the poles which are closer to imaginary axis has more effect on the output. So we can call it as a dominant pole compared to the other pole which is far away from the origin or imaginary axis. Clear? Yeah. This you keep in mind, because this hereafter you will use this times dominant pole, something like that. So the thing, these all stories has to come in your mind. Okay, dominant poles are poles closer to imaginary axis, which has more effect on the output response. Okay, clear. So now what we'll do is, our aim is to study the effect of zeros in a system. So in this system there is no zero. So obviously in the second system we will take one 0. Let it be y of s divided by u of s, which is equal to the same system s plus 1, s plus 10, but I have a 0 at s plus 2. Okay, so in this case m is equal to 1, n equal to 2. So here also n is greater than m, so it is a strictly proper transfer function. What about the poles of this system? Poles remain same. They are at location -1 and -10, but we have a 0 at -2. So all the poles are on the left half of the spline. So the system is a given system is a stable system, because we don't need to worry about the 0. As per the study, the location of poles will determine the stability. Now we will see, we have added one 0. Let us see whether this 0 is affecting the stability or not. Okay, so that again you can derive the unit step response. So we can write y of s is equal to s plus 2 divided by s plus 1, s plus 10, The same analysis you can do. Apply partial fraction a divided by s plus b divided by s plus 1 plus c divided by s plus 10. Right now, compared to previous problem, we have a term on the left side. That is the only difference. This is because of the zero, right? So, how will you find ABC? The same method you can follow. You find and tell me what is the value of A, B, and C. So, what is A? What is B? What is C? And C is minus 4 by 45. Okay, I am writing like this. This is 8 by 90 because previously we got A equal to 1 by 10, B is equal to 1 by 9, C equal to 1 by 90. So I am writing 4 by 45 plus 8 by 90 just to compare both equations. Okay, so we can write y of s is equal to 1 by 5s minus 1 by 9 s plus 1. Oh, sorry. Okay, it's correct only, right? Yeah. This one also minus only, right? Minus 4 by 45, right? Okay, so we can write 8 by 90 and divided by s plus 10. Right? So, if I take inverse Laplace transform, you can get the unit step response. Y of t is equal to 1 by 5 minus 1 by 9 e power minus t minus 8 by 90 e power minus 10. So this is the equation. So I have two responses. Let this be equation number 1 and let this be equation number 2. So what are the observations? If you compare both the equations, what are the observations? Can you tell? Previously, our steady state value was 1 by 10, right? In the same system, you have added one pole at s equal to minus 2. Whether you are getting the same steady state value? Yeah, in this case, the steady state value is 1 by 10. Sorry, 1 by 5. Previously, it was 1 by 10, right? So, one of the observation is steady state value is changed after adding the 0, right? And another observation, what about the coefficients of exponential terms? Previously it was 1 by 9 and minus 1 by 9 and 1 by 90, right? But in this case, this one of the coefficient is changed to 8 by 20, right? So another observation is after adding a 0 to the same system, coefficients of exponential term are changed. Why it is changed? Because that 0 is affecting the residue of the system, right? Your residues are changed because of this 0. So we can write it affects 0 affects the residues of the system. So it is affecting the steady state value. It is affecting the coefficient of exponential terms. It is affecting the residue of the system. Okay. What about the exponents of the system? Both system, equation number 1 and 2, exponents of the exponential term. Remain same, right? Exponents of the exponential term remains the same. So what you understand from the fourth point? If exponents remain same means both the systems are having one pole at -1, another pole at -10. So it is not affecting the location of the pole, right? So the 0 is not affecting the stability of the system. It is affecting the steady state value. And one more thing is, we will come to the same discussion what we have done for the first case. So we have two terms, right? 1/9 e power minus t. Another term is 8/90 e power minus t. So if we draw the characteristics of these two terms with respect to t, the first waveform, what will be the, it will start from 1/9. Then it will decay exponentially. When t turns to 0, it will goes to 0, right? So what about the second one? What about the second one? This 8/90 will be closer to 1/9, right? Previously it was very far like this. It started from 1/90, but in this case it is 8/90. So obviously it will be starting from somewhere here. So 8/90. Again, it will decay exponentially and will come to 0. So that this is the observation. So what you understand from this graph? If you compare both this, in this graph, you understand that the pole which is closer to the imaginary axis is dominating the output, right? So after adding the 0 in the transfer function, what you observe from this graph? Yeah, that means this 0 is, the effect of 0 is decrease the dominancy of that pole, right? That is the meaning. So this one is 8/90 e power minus t. Now this also come closer to this red. So that means the dominancy of this is decreased due to the effect of 0. That is the meaning, right? Is decreased due to the 0 s plus 2. Correct? So if we draw the location, real part, imaginary part, I have one pole at here, one pole at here, and I have one 0 at this point, right? This is -10. So if I insert a 0 here, the dominancy of this pole is reduced. That means the 0 is affecting the dynamics of the system, right? It is affecting the steady state value as well as dynamics of the system, but it is not at all affecting the stability of the system. Clear? So that is the conclusion. So what you can do is, if I move this 0 value further closer to this, what will happen? You can imagine. In other way, what I can tell is, it is closer to 1 in the sense the transfer function, say your transfer function becomes, instead of s plus 2, it is s plus 1.8 divided by s plus 1, s plus 10. And again, if you move your 0 further, s plus 1.9 divided by, sorry, and reduce it. We can move closer to that. Some 1.3 divided by x plus 1, s plus 10. If you move further, what will happen? S plus 1 divided by s plus 1 to s plus 10. So what you understand from this? If you move your 0 further closer to the dominant pole, finally, at this point, your dominant pole means 0 is equal to pole, right? Because in this case, you are having 0 at minus 1. You are having poles at minus 1 and minus 10. Here, it is 0 at minus 1.8. Poles at minus 1, minus 10. In this case, 0 is at minus 1.3. Poles at minus 1, minus 10. Okay. So what you can observe from here? Can we do any mathematical analysis in this? You see here? Because both are same, right? You can cancel it. There is a pole 0 cancellation at this condition, right? So if you do that cancellation, you will get the transfer function as 1 by s plus 10. Correct? So what is the observation from here? What is the order of this system? What is the order of this system? First order system. This one. Before, before cancellation, it was second order system, right? So when your pole is equal to 0, this pole, the pole at 1 is cancelled by the 0 at 1. So this is called pole 0 cancellation. But after the cancellation, you can observe that the second order system is the system. What is the order of this system? This is a first order system, right? So this process is called pole 0 cancellation. What is the effect of pole 0 cancellation? The second order system is converted to a first order system. So this term you keep in mind, pole 0 cancellation. Usually we will not use this concept typically. Anyway, that we will discuss later. So the concept of pole 0 cancellation, please keep in mind. Hope everyone understood the concept. So if you add a pole to the left side, and one more thing is where we have added the pole. We have added the pole in the left hand side of the spline, right? So after adding a pole to the system, it is affecting the steady state value, it is affecting the dynamics of the system, and the dominancy of the pole, which is closer to the imaginary axis, also reducing. So finally, when the pole is equal to 0, the dominancy of the pole got cancelled by the 0. So further, this second order system became a first order system. So these are the observation. Okay, it is not affecting the stability of the system. Now one more analysis we will do. What is that analysis? You have to see what happens when the 0 is added to the right hand of the right. We'll reconsider the same problem. Like poles remain same location, s plus 1, s plus 10, and let it be in right side, s equal to, sorry, s minus 2 divided by s plus 1 to s plus 10. So in this case also, n equal to 2, m equal to 1, it is a strictly 177. Now check it once. Is it okay? So what are the poles? We have poles at -1, -10. The only change is 0 is at +2. So if we draw the graphical representation of this system, take S plane, this is real part, this is imaginary part, convex plane. We can place our poles first. This is -1, which is closer to the imaginary axis compared to the other pole, -10. Okay, this is origin. So what about the 0? We have a 0 at -2. Sorry, +2. It can be represented in a small cell. Okay, clear. Now we will do the same analysis. Find the unit step response of the system. Unit step response of the system. So that we can write y of s is equal to s minus 2 divided by s plus 1, s plus 10. We can write this as applying partial fraction a by s plus b by s plus 1 plus c by s plus 10. So please tell me the values of residues. So the left hand side becomes s minus 2. A multiplied by s plus 1, s plus 2 plus b s plus 10 plus c s plus 1. So please tell me the values. C equal to 12 by 90. Okay. Okay, fine. So we can write y of s is equal to minus 1 by 5 plus 1 by 3 s plus 1 plus, it's a plus or minus? C.
Minus.
Sorry? Minus only, right? Oh, okay. Yeah. Minus 12 by 90 s plus 10, right? So after taking inverse Laplace transform, we can obtain the unit step response, that is y of t is equal to, here s is there, minus 1 by 5 plus 1 by 3 e power minus t minus 12 divided by 19 e power minus 10t. So this is the unit step response. You compare the previous response. What are the observations? So this is the unit step response. What are the observations? First of all, the steady state value becomes negative, minus 1 by 5, right? Okay, anyway, we will come to that point later. What about the coefficients of exponential time? Changing. Another observation is coefficients of exponential times are changed. Okay, what about the exponents of the exponential time? It remains same like the previous. Exponents of the exponential time remains same. So that indicates the pole are at the same location, right? So here also we can see that if you locate your zero on the right hand side of the S-plane, it is affecting the steady state value, it is affecting the coefficients, that is, it is affecting the residues, it is not at all affecting the exponent times, right? So that means this also affecting the steady state value as well as dynamics of the system. It is not affecting the stability of the system, right? So another thing is this, you keep in mind anyway. The simulations and all, for the same problem we will do MATLAB simulation last, and I will show the waveforms. So if you draw the response of this system with respect to t of this system, so it will start from which point? Zero only, right? Because as per our assumption, initial conditions are zero, so obviously it starts from zero. And our input is plus 1. That is a unit step. Our analysis response will go to negative. Right? So this will be the shape of the waveform. Initially, there will be a portion on the positive, then slowly go to steady state value. This is steady state, it is minus 1 by 5. This a small positive portion will be there. Yeah, 1 second. We share it. Yeah. Check it once. Fine, yeah, okay. So this is the observation. The curve starts from 0 at time t equal to 0. Then initially a small positive value will be there. Finally, what will happen? It will slowly decay, will go to the negative steady state. Well, initially a positive will be there. So this will be the nature. So if you add S0 to the right hand side of the S-plane, the response will start from the origin in positive direction or in one direction, and then it moves to the other direction. Yeah, finally it will settle at some value. So that will be the nature of the zero. Okay, so this kind of zero means zeros in RHP, right hand plane of the S plane, is called non-minimum phase zeros. Non minimum phase zeros. Okay, this term you keep in mind. This term frequently we will use for the, so non-minimum phase zero means it is a zero which is placed at the right hand side of the display. Clear? Hope everyone understood the concept, means what is the effect of zero in a system, because these are not very important for the hereafter, means last unit we will discuss about design of controller for a system which is having pole, zero, many things will be there. So by the time you have to know what is the effect of zero in a system. If you move your zero, what will happen to the system? Because zero, if you move, in previous problem we have seen that if you move your zero from -2 to moves towards the origin, what is happening is it is not affecting the stability of the system, but it is affecting the dynamic of the system by changing the residue of the system. Otherwise, changing the coefficients of the exponential terms in the response, output response. Clear? So if you have any doubt, please ask. We will wind up the class today, today's class.